Okay, so I'm gonna do a quick kind of informal representation of my master's project. In my infinite wisdom, when I presented it live, I of course did not remember to record the Zoom session or anything, and I didn't have anyone else recording it. So that's great. So I kind of wanted to just have a record of it, just kind of have an archive of these slides, but kind of explained. Like I said, this is going to be very informal. I still want to get all the ideas across and just give a brief kind of overview of my project. So we'll just go through these slides real quick, informally, and just kind of bang it out. We'll get some interesting math and data science topics. So I worked on something called topological data analysis of electrocardiogram signals. So we will kind of look at what this consists of. So the contents of this presentation, we're first going to look at electrocardiography as a whole, and then kind of these ECG signals and what they are exactly. Then we're going to look at topological data analysis kind of in a nutshell, at a high level, and just kind of give a brief overview of what that is and what that entails. Then we're going to shift gears a little bit and look at some kind of basic foundations from algebraic topology, simplicial complexes and homology groups. Nothing crazy. And then we're going to shift gears again and look at metrics on probability measures and distributions and what those look like. And then we're going to look at some interesting results and applications. There wasn't really anything novel here that we did, and like we didn't get any novel results. It was just kind of like, here's some things we can try and let's just see if we can get any kind of results. But by no means is this like groundbreaking or novel research. So first we'll look at electrocardiography. So ECG signals measure kind of the electrical activity of the human heart. So they're captured using 12 leads on a patient or subject. So there's 11 of these physical leads. So these physical leads are just little sensors that are hooked up, on the subject in 11 different places on the body. And then we also have one virtual lead. And so this virtual lead is an algebraic combination of, I think, 2 or 3 of the other leads. So that once they record 2 or 3 of the signals of the other leads, they do some math and combine them in a way that gives us another virtual signal. And so typically these samples are, they span over 10 seconds and 1,000 equispaced nodes. And then electrocardiography in general is just kind of like the analysis. Well, it's not kind of, it is exactly the analysis and interpretation of these signals. So like it gives cardiologists an insight into kind of what's going on with the subject's heart. So we're kind of going to look at maybe a non-traditional way to look at these signals and see if anything interesting comes of it. So here's kind of just a quick example of where some of the leads might be placed. So you can see there's like 2 on the ankles, 1 on each arm, and then a bunch kind of more central to the heart area. I don't even think this one has all 11 on it, but this is just like, this is, just maybe a quick interpretation or visualization of what it might look like and where these leads might be placed. But these are pretty standard. And so ECG signals in general have these 5 major features that kind of tell us different properties. So we have this Q wave in yellow, we have the R wave in red, and the S wave in this purple. And so depending on the length and height and depth of these different segments can tell clinicians can give them insight into things. And then same with like these intervals. So we have this PR interval on the bottom, this QT interval on the bottom, and this ST segment, and this PR segment. So same thing, the length of these, there's some interpretation there where, the length of these things and the depth and everything gives some kind of insight into what's going on with the heart. So here is just kind of a basic plot, just so we can kind of get a visual of what these signals look like, when we put it on paper. So these are just 2 different leads from a random patient. So I just sampled 2 random leads. So this is kind of what it looks like. You can see at the bottom we have, just 1,000 data points. We don't really need to worry so much about the y-axis and what that's measuring right now. In general, that's some kind of electrical output. But for us, we'll see that that unit doesn't really matter because we're going to take a different interpretation of it and look at it for more of a mathematical versus engineering side of things. And so we kind of we had, some hypotheses. And so, visual inspection of these ECG signals is only so good, right? It only goes so far. And so we want to see if there's some kind of rigorous mathematical analysis we can do on these signals that gives more insight than maybe just someone sitting at a computer and looking at these things. And so we kind of wanted to look at a couple questions and say, okay, is it possible there's high dimensional topological or geometric patterns or features in ECG data? And then if so, how can we impose and construct the geometry on this data? And then what do these patterns and features possibly suggest? So are there geometric patterns? If there are, how do we impose that on the data? And then if we can impose it on the data, let's look at these features and, well, what do they actually mean in the context of electrocardiography? So we think that with the right interpretation and analysis of ECG signals, we can actually get some results or insight that is not clear from the standard methods of just like visual inspection. I know there's other methods too, but this is just kind of maybe something that's a little more non-traditional. So now we're going to just kind of shift gears a little bit and look at topological data analysis kind of as a whole. I'm just going to call it TDA from now. So TDA is a means to analyze higher dimensional data, by looking at topological and geometric features or patterns and kind of the interpretation of such. And note that the data itself does not need to have geometric, it doesn't need to have like a physical geometric interpretation. So this isn't necessarily data that's captured that's known to have a geometric pattern. This data can be very abstract, and then we kind of can impose geometry and topology on it. So it doesn't need to necessarily be captured as like shapes or anything like that. So TDA is a great tool for looking at data that lives in high dimensional space and maybe lives in non-Euclidean space, which is great because sometimes we have non-Euclidean features that can give us insight, and we want to look at those things and see and do analysis on them. So it's great for analyzing non-Euclidean things. And then it's great if we don't want to do any kind of dimensional reduction. There are a lot of great dimensional reduction methods like PCA and all of these other, there's a lot, but sometimes depending on the method and the type of data, it's possible to destroy or lose geometric and topological information when we do that. And so this is how, okay, well, can we leave it in its can we leave it in this high dimensional space and not lose any data, but still be able to analyze it effectively and efficiently within reason. So there's kind of a traditional pipeline for what TDA might look like. Excuse me. So first we're given some kind of data, right? Obviously we're doing this numerically, so it needs to be discrete and finite. And then we slam this data into a pairwise distance matrix. And so we can choose, so we need to impose a matrix. So once we have this data, we build a piecewise linear manifold on top of it with respect to that metric. And so we get some kind of continuous structure, but we kind of still get homological and homotopic properties from this data. So even though we kind of are going from discrete and we're kind of making a discrete data, but we're kind of making a continuous mesh on it. But a lot of the, homological and homotopic features are going to be preserved. And then once we have this manifold, we look at these features of interest and see which data points are associated with such features and see what those data points have in common and say, okay, well, does the homology and homotopy of this thing actually give us any insight? And it's possible it doesn't, but we're looking at, well, hopefully it does. But in general, TDA is very sensitive to the choice of the metric. We want to, given the data, we want to use a metric that makes sense. There's been instances where I've seen people use like a correlation, like linear correlation as their metric. So that's just an example of something that might seem a little abstract, but we can still impose geometry on, on just more abstract statistical data, as long as we have a good metric. Then it doesn't matter. This data can be really abstract, and as long this metric really just measures some kind of correlation or correspondence. It doesn't necessarily have a real world geometric or topological implication on what this data looks like. So I want to make that clear. That this, I said it before, but this data does not need to already be geometric in nature. It can be any kind of data that we want to find correlation with, and we just choose some metric that we think will be good for this data, and then we go from there. So this is kind of just a quick visualization of what this pipeline looks like. Oh, excuse me. So the input is usually, so you can either use like a point cloud with some kind of clustering function or algorithm. That's not what we did here. We just gave it this pairwise distance matrix. So you can go either way, but it's not uncommon to use a point cloud and some kind of clustering algorithm. That's not uncommon. Or sometimes a distance matrix is easier to construct, and in our case, that was the case, and so we just did that. And then there's typically three different structures or complexes that can be built on top of this. So we have like these geometric complexes, which is what we did. Then we have something called a cover complex and a cubical complex. They're all pretty similar. We don't really need to go into too much detail. The cubical complex is kind of what you'd imagine. It's kind of looking at how, like, using just strictly cubical features and structure, how can we look at this thing? Where a geometric complex uses just kind of abstract simplices in general. We'll talk about that in a second, what that means. And so once we have this complex built on top of this data, we want to look at, there's three different things we can do with it now. We can look at the representation of it, we can do something called the filtration, or we can simplify it and make it easier to analyze. So I haven't gone too deep into the simplification or representation. So we used the filtration algorithm on this, and we'll see what that looks like. But filtration is pretty common and pretty popular, and it fits for most data. And then so once we have this filtration, which I'll talk about what does that mean exactly. But from this filtration we can look at something called the persistent homology, or the reconstruction of this manifold. Once again, this choice is pretty heuristic depending on the type of data. In our case, we used persistent homology, which we'll see is a great tool. And then there's all these different ways to analyze this, right? We can visualize it, look at more geometric stuff, or look at more statistical stuff. So in our case, we mostly just are looking at the visualization of the persistent homology. But of course, going down the geometry and statistics of this is a huge rabbit hole. And so, there's a lot of interpretation that can be drawn from that if we dive into some deeper geometry and statistical analysis. But for now, that was kind of beyond the scope of our project. I don't know, given more time, maybe I'd be interested in doing some more geometric topology analysis on it. But for now, we're just going to look at visualization, which is nice, easy. So, kind of going back to that previous slide where we talked about how do we know which metric is best. And so, assuming we have an appropriate metric, that's great. But then it's like, okay, well, how do we use this metric to actually impose the geometry on this data? And so this is where we're going to talk about and use something called simplicial complexes. So these are a great way of identifying homological and homotopic features of discrete or continuous data. So we're going to look at that. And it's a great tool in algebraic topology and, in data analysis in general. But there's a lot of math behind it, so we're going to kind of shift gears a little bit and do an algebraic topology primer, just to look at these simplicial complexes. So these are kind of the building blocks of TDA. And so if we have a set of affinely independent points. A K-simplex spanned by this set is the convex hull of this set. And so, just a reminder, the convex hull is the smallest convex set that contains all the points. So a K-simplex is just the convex hull of some number of points in X. So yeah, it's the smallest convex set that contains these points, right? And so a simplicial complex, I'll denote this capital K, it's a collection of these simplices such that the face of any simplex is also a simplex, which sounds a little weird. I'll talk about it in a sec. And the intersection of any two simplices is either a common face of each simplex or it's an empty set. And so this seems really abstract, but I'll give some more interpretation and visualization, and it should make a little more sense. So we talked about faces just barely. So now we're going to talk, give a rigorous definition of faces. So we can kind of look at this for people. I don't know, if you come from like a combinatorics or graph theory background, a complex, right, is just kind of some kind of graph that lives in some metric space. So we will represent a simplex here just by the sigma with these points. And the points of X, these are the vertices of sigma, and the simplices that are spanned by these subsets are the faces of sigma. I know that's still a little abstract, but there will be a nice visual interpretation. So in lower dimensions, right, for K, 0, 1, 2, 3, maybe even 4, it's pretty easy to visualize these things. But, arbitrarily, it's not really possible. Like, how are you going to visualize, a 12 simplex? Yeah, you're not. But, we'll give a reasonable representation for lower dimensions, and then that will give you a good enough interpretation of what's going on. And then that generalizes to what, n-dimensional space. So here's a great, I got cut off a little bit at the bottom, but this is just here. This would be an example of a simplicial complex. So we have simplices of 0, 1, 2, and 3 are all pictured. So a 0 simplex here would just be a point. Okay. 1 simplex is just a line segment connecting 2 points. A 2 simplex would be like this triangle, like, right? This is a simplex, a 2 simplex. And then this 3 simplex would be like this tetrahedral looking thing, or this this triangular prism thing. And so recall that the face of a simplex is also a simplex. So if I have this 1 simplex, or I should say the vertice, each vertex is also a simplex. So this line segment is a 1 simplex, this vertice is a 0 simplex, this vertice is a 0 simplex. This guy is a 2 simplex, right? And then each edge and vertex is a simplex. So this 2 simplex, it has an edge here that's a 1 simplex, it has an edge here that's a 1 simplex, it has an edge here that's a 1 simplex. And then for this 3 simplex, this pyramid looking thing, right, each face is a 2 simplex, is a triangle, right? So here's another triangle, like 2 simplex. And then from that triangle, right, each edge is a 1 simplex, and each vertex here is a 0 simplex. So that's kind of that's a general, that's a visualization for smaller dimensions. So what I really want to get at is that the face of a K simplex is like a K minus 1 simplex. Is really what I want to get at, or like an edge sometimes is what they're called, like, or yeah, edge or face are used interchangeably. So that's kind of a quick rundown of 0, 1, 2, and 3 simplices and what they look like. It might still seem a little weird, but it's you might be overthinking. Like, it's as simple as it seems, right? It's just it's just kind of like this hierarchical structure where the face of a K simplex is a K minus 1 simplex. That's kind of the most important part. So in that kind of flowchart, we talked about something called the filtration. And this gives us a way of kind of reconstructing and looking at some geometric features of this data. And so there's a lot of different kinds of simplicial complexes. There's lots of different classes of them. So the definition is explicit, but there's a lot of things that fall under, um, under the definition of a simplicial complex. So the one we looked at, this is a really common one, is the Vittorius-Ribbs complex. And so if we have some set of points in our metric space, and then some parameter alpha, or sometimes we call this like a radius, the Ribbs complex is just a set of all these simplices such that the distance between any two simplices is less than alpha. So to kind of see what that looks like, so here on this chart, or on this graphic, we see, so alpha is the radius of these yellow circles. So right here I have a 0 simplex, and it's saying I'm going to blow this thing up to a radius of alpha and see if it touches anything else. Well, this one doesn't, so he stays as a 0 simplex. But let's look at this point and this point. If I blow these guys each up to a radius of alpha, and I blow him up to a radius of alpha, we can see that they intersect a little bit. And so because they intersect at this radius of alpha, we connect them and make a 1 simplex. And so here we can see an example. Well, these guys are alpha apart, so they get combined. And then I have these other 3 guys, and you can see there's small intersections here. And so they all get joined into a 2 simplex. So what happens is basically we choose this alpha, which is kind of like the radius of these balls, and that will tell us how to attach these things and how to construct these simplices. And then of course, this alpha is with respect to the metric that we chose. So here in this picture, it's Euclidean, but that doesn't need to be the case. But this is a great way of saying how far apart or how correlated do I want these things to be before I consider them to be part of a simplex or a simplicial complex. So I know that's a lot, but the idea is I have some data, I can construct this Ribbs complex on top of it, and that will give me some idea of distance and correlation. So this right here is just a quick, dirty example of a Ribbs complex on this data set of these little red points. And so, right, we can see 0, 1, 2, and 3 simplices form when I make alpha big enough. So that's the idea here. So we're going to look at something a little different, but these will become apparent in a sec. So we're going to look at, chains and cycles. So in general, a K chain is just a linear combination of K simplices. And then a chain is a cycle if it has an empty boundary. And so chains and cycles are used to explicitly define homology on simplicial complexes, which is great. And now I'll show you how they define that homology. Well, I guess here's a quick example. So here on the left, this would be like a 1 chain, right? Because it's a linear combination of 1 simplices. So on the left, it's a 1 chain, right? It's just a connection of a bunch of 1 simplices. And then on the right would be a cycle, right? So it's a K chain, but it doesn't have a boundary, right? The boundary on this guy is empty. On the left, the boundary would be like A6, A1, or whatever. But the guy on the right has empty boundary. So that's a 1 chain, and then we call this a 1 cycle. I don't remember if this is technically an algebraic or geometric cycle. I don't think it's important necessarily for the sake of my project, but yeah, I'll just refer to it as a cycle. And so like a 2 chains would be like a combination of a bunch of 2 simplices. So it would look like a linear combination of a bunch of these triangles next to each other. And then if that guy has empty boundary, I would get a 2 cycle. So that's the difference between cycles and chains. But right, for K equals 1 and K equals 2, it's pretty straightforward. And it's fine to just think about this when we generalize it to higher dimensions. So we can actually need to do a little bit of math on these guys explicitly. As much fun as pictures are, it doesn't give us a good enough rigorous definition in general. So we write these chains as finite sums of simplices, right? So a one chain is just a sum of a bunch of one simplices, and then like that picture we just saw. And then so here we usually just will let a k chain be defined as this variable c, where a is just z mod 2, and then sigma is the vertex or face of this simplex. And so it's z mod 2, so we can just, a is 1 where this thing is connected, and then it's just 0 elsewhere. So it's kind of like an indicator, almost like an indicator function. And then addition of addition of these guys is well defined. It's really straightforward, like we saw. It's easy to take two one simplices and connect them, right? If I have a line segment and a line segment, I can connect them in the middle with another one. So that's kind of the addition of chains. And so here, if I have two chains, C1 and C2, with the given prime coefficients, AI and BI, and then the simplices, I can just add these together by just adding the prime coefficients, or the prime field coefficients at each point. So I just take A plus B mod 2 sigma I. So it's really straightforward. And this is great because this addition actually induces a group structure on these guys. Oh, I misspoke. Yeah, sorry. Sigma sub I is a K simplex. I think I said face or something, but it's a simplex. And so we come to this lemma. I think this is from Hatcher, maybe. So if I have a simplicial complex K, if I take the set of all K chains on this thing, so remember chains are just connections, right? Exactly what you would think they look like. So if I take this set of all the K chains over big K, let's call that guy C. So I collect all the chains. And then if I take this C with this addition operator right above, this actually forms the free abelian group. And so it's pretty straightforward. It's abelian because this addition operator certainly commutes. And then it's free because I can take these AIs to be in any prime field I want, and I can scale them by any field coefficients. So that makes it free. So it's pretty like the abelian, commutativity of it is easy to see. And then, and it being free is also pretty straightforward because I can take these prime fields, or I can take these coefficients from any prime field I want, and that that will make kind of will give me some kind of notion of a span. I'm talking fast. Sorry. So given this group C, so this is the group of all K chains on a simplex. We have a boundary operator on this group. So the boundary of a K chain is the sum of the boundaries of its simplices. So I know that sounds like a lot. So if I have my AI coefficients in Z mod 2Z and a K simplex sigma I, the boundary operator will take this guy and reduce, we'll basically reduce it. So what I really want, I know that definition might look a little weird, but what we really want to drive home is that the boundary of a K chain is a K minus 1 chain. And I think I talked about that when I gave the example of a one chain and a one cycle, right? So the one chain was this guy, and the boundary of that guy was a 0 simplex, right? Because it was just these 2 points. And then, so the boundary of a K chain is a K minus 1 chain. That's really the big idea here, and that's what I want to drive home. And this boundary operator actually induces a homomorphism from the CK group to the CK minus 1 group, which is pretty cool because it's not super straightforward. It's obviously not an isomorphism, but we do have this homomorphic structure, which is awesome. It makes things convenient. So given this group CK, so this is the group of all K chains, there's two other subgroups of this guy that are of particular interest. So we can look at the subgroup of all K cycles of this thing, and we call this Z. So ZK is the subgroup of all K cycles. So remember, cycles were like The one cycle just was kind of, it was just homotopic to a circle. And then BK is a subgroup of ZK, and that's the subgroup of all K boundaries of K. So that's all the K simplices that are boundaries. And so specifically, right, that this group ZK, it's the group of all K chains that vanish under the kth boundary operator. So I hit this guy with the boundary operator K number of times, and all the K chains that vanish under that guy form this group ZK. And these three naturally give this hierarchical structure. This is just called the fundamental lemma of homology, where, right, so BK is a subgroup of ZK is a subgroup of CK, which is great. And this kind of gives us also an intuition on how chains, cycles, and boundaries kind of connect, which is pretty cool. So we can see, so I have chains. From chains I get cycles. From cycles I get boundary. That's kind of the idea. So given this fundamental lemma of homology, we can now construct something called the kth homology group. The kth homology group of a topological space, it's the kernel of the kth boundary operator modulo the kernel of the k+1 boundary operator. And that, if you're not familiar with algebra, or you're not super good with algebra, like I'm not, or whatever, it's easier to just look at, okay, this is actually just ZK modulo BK, or quotient out the BK. And so what this means is the kth homology group is really just the group of all these K cycles modulo the extra K boundaries that might be floating off. So I take all these K cycles, chop off any boundaries, and that's makes this kth homology group. But if you want, you can dive into the kernel modulo image definition. That's good for more abstract notions, but for us it's fine to just think about it as the K cycle group modulo the K boundary group. It's totally fine. So now we're going to look at something called BT numbers. So BT numbers are kind of a way to summarize the homology groups and the homology of a topological space, which is great. So the definition, the kth BT number of a topological space is the rank of its homology group. So that's right, that's the size of the largest linearly independent subset. And it can also be seen as just the difference of the rank of ZK, the cycle group, and BK, the boundary group. So in a nutshell, I mean, this is fine for our definition, but the kth BT number, tells us the number of K dimensional holes in that topological space. So if the first BT number is 2 of a topological space, that means that there are 2 one-dimensional holes in the space. So the BT number is an integer, right? And then it's like the kth BT number. So there's 2 kind of integers we associate with this. The K is the number, or the K is the dimension of the hole we're concerned in, and then the BT number is how many of those K dimensional holes. So looking at a topological space, we can look at the first BT numbers, the second BT numbers, the third BT, all the way up to whatever. So that was a lot of algebraic topology, real quick, but the kind of flow I want to get through to you is that from simplicial complexes, we get chains and cycles. From these chains and cycles, we can get homology groups. Then given these homology groups, we get BT numbers. So just given simplicial complexes as an input, we can automate some stuff and get BT numbers as an output, which kind of summarizes the whole space topologically, which is awesome. So now we're going to look at, okay, well, what does this homology mean and how do we actually interpret it? So one of the biggest tools or principles in TDA is this idea of persistent homology. So this is a tool that tracks the homology of a space as I change the complex. So remember, the complex has this alpha parameter. We can think of it as a radius of these balls. So as I make this alpha bigger, so as I blow up this radius bigger and bigger, how does the homology of this thing change? So in this first picture here, we can see this will be where alpha is 0, right? I just have a point cloud. But you can already see there's kind of two features that I'm probably interested in, right? And so first, as I increase alpha a little bit, that means I'm going to draw a ball of radius alpha around each point, and those intersections, if the alpha ball of 2 points intersects, then I connect them and make a simplex. So in the picture in the middle, this is where I varied alpha a little bit more, and we start to see some connections. And we can see on the right, we actually get a nice one cycle. And then on the far right picture, if I increase alpha a little bit more, I actually get some connected components all around, and then I can see I have 2 one cycles pop up. So I have this larger circle and this smaller circle off to the right. And so in the context of BT numbers, I would say the first BT number of this guy is 2. So the number of one-dimensional holes this guy has is 2. So that the first BT number, I'm looking at the guy on the far right, the first BT number of that guy is 2. So we can see as alpha increases from 0 to whatever, we can see that these homological features are kind of born. And you could even see if I increased alpha more, that the small hole would eventually kind of close up. And then if I did it, if I increased alpha, really big, then even that larger hole would eventually close up. And so as I change this alpha, the homology of the space changes with it. And so at each point in alpha, I want to see what is the homology of the space, and I want to track each feature and see what's the alpha parameter that made this thing appear, and then how far does that thing live before the alpha parameter destroys it. So there's another way to interpret this visually. So in general, right, like that's fine in R2 or even R3, we can visualize it, but in general, it's not easy to just draw a picture. But we have these things called barcode charts and persistence line graphs. So this is a graphical way to represent things, and this is great for when we can't visualize it in an arbitrary dimension. So, excuse me. So on the left here, looking at the barcode, this is my preferred diagram. So the filtration value on the x-axis, that's my alpha parameter, my radius, right? Index of feature, that doesn't matter for now. But what I want to drive through is the red bars are the 0 homology features. So these are just connected components. And then the blue, that's the one-dimensional homology features. So the holes, right? And so you can see, and then it's as this alpha evolves. So you can see on the left that I have a bunch of these connected components that are born. And then in that diagram, I had 2 pretty obvious cycles, right? 2 pretty obvious holes. And so I can kind of see that in this persistence barcode, right? I can see that this hole lived for a little bit, right? He was formed at this alpha. Once I blew alpha up a little bit more, then it was destroyed. And then this guy was the bigger hole, so once alpha was around 1, this thing, and then as alpha increased, it just kind of balloons. And then persistence line graph tells me the exact same thing, but here it's the birth and death time with respect to alpha, and so this line. So the idea is the further off this line a point lies, that's the longer its lifetime, and so it's more significant in that case. So you can see here from the persistence diagram, I have these 2 points, or these 2 significant blue homology features, and then the persistence line graph, it's this guy and this guy. That corresponds to this guy and this guy. So that's a quick graphical way we can look at these things without for general arbitrary dimensions. Uh, look at kind of another example. So we just saw that example in R2, but now we want to look at something with a non-Euclidean metric. So we're going to take that same example, but we're going to look at it just on the unit sphere. So I have these two circles, and then I pulled this one down and just shifted it down a little bit. And what I really want to see is, with respect to this new metric, I should see persistence graphs that are the same as the other one, right? I should have two distinct homology features. The radius values might change because this is the unit sphere. But I should see two distinct homology features once again, because it's the same example, just with respect to a different metric. But we took that into account when calculating it. Oh, whoops. And so then we'll see later that we should have the same homology. So using the metric on the sphere is not necessarily trivial, but you can do a little bit of linear algebra, and you can come up with this cosine metric. And so this is just the geodesic distance on the sphere. Nothing crazy here, just some linear algebra. You can come up with this pretty easily. And so using this metric, we looked at the Rips complex of this thing. And like I said, we expect these graphs to look like the R2 example, because it's the same kind of homology, but just in a different metric. So if we move over, well, we can see exactly what we want. So I can see, like I said, these points are going to be different because we were on the unit sphere, so the alpha value might look a little inflated or whatever, or deflated. But I can see here I have a distinct one homology feature, and then here I have a distinct one homology feature, which is good, right? That's consistent with the R2 example. And then here I have the same first small hole and the second small hole, which is great. So it is consistent. I used, a different topological space, and a different metric, but the homology gave me these same examples. So that's just kind of like a sanity check to be like, okay, TDA makes sense, and it's legit, like it actually works. And so that's the idea here. And once again, when alpha is around 0.1, this thing has a first BT number of 2. So it has two one-dimensional holes when alpha is about 0.1. So now we're going to shift gears again and look at ECG signals as probability functions. So we had all these ECG signals, and we're going to treat them as probability mass functions. The motivation behind this was, I don't know. We thought it would be interesting and it might work, but there was no really clear. We just kind of chose it because there wasn't like a clear motivator or factor for it. We're just like, let's try this and see what sticks. So we'll come up with this mesh xi, which will be, just 1,000 samples. And then we'll just have a corresponding amplitude or function value, at this point, just some function f. But we need to make some changes to these ECG signals first to make them probability functions, right? ECG signals may have negative values, and so we took care of this just with this vertical shift, right? So we just took every point and just shifted it up by the minimum, which is straightforward. And then, right, probability mass function is also assumed to be normalized, so we had to just normalize each signal by just scaling it by this amplitude, which is also pretty straightforward. And so now looking at metrics on this guy, so we have these signals which are going to be like our data points, but we need a reasonable metric between these guys, right? So thankfully for probability distributions, there's a couple more intuitive metrics. The one we are going to look at is the Wasserstein metric. So this looks like a lot of functional analysis crap, but it simplifies nicely for our case. So if I have a complete separable metric space, I think some definitions even say this guy needs to be a radon space, which is, equivalent. But here we're in R, so it's fine. So it's definitely a radon space. And then for some order P, the Wasserstein P distance for two probability measures, so we'll call them like mu and nu, with finite moments is given by this guy. So, right, it's the infimum over the expectation of these joint measures with this metric P. And then to the 1 over P. So it looks LP-ish, just in the fact the way we choose the way the order P changes things, but it's the expectation times this scaled by this metric. And this, here gamma is all the joint probability measures on the product space with the respective marginals. So in general, Wasserstein distance is not easy to compute or understand for arbitrarily large P. And because of this, it's pretty common in practice to use the order of P equals 1 or 2. We did 1, and that's totally fine. For our data was not too crazy. So when P equals 1, the Wasserstein distance gets simplified very nicely, where we just kind of have this integral over the density, over the difference of these density functions. And it's important to note that this metric actually is Riemannian, and so that makes sense for us to have. So that gives us some geometric intuition, right? So if I take the set of all these probability measures with this metric, certainly it forms a manifold, right? Probability measures map from something to R, so the atlas of this guy is pretty trivial. And then with this Riemannian metric, so certainly it forms some kind of Riemannian structure. So that's for continuous measures, but in our case, of course, we have discrete measures, but there's still a natural way to do it. We just kind of take the integral of each interval with an ordered set, where these are where we just take into account the discontinuities of the CDF, of the density function. So now we have some more ingredients, right? We have some signals. We have a good metric that we're going to use. And so given this now, we have these signals as data points. We have a Wasserstein metric, and we want to put those together and see what TDA spits out. So before we look at ECG signals, we wanted to look at another time series just to kind of make sure, just as like another sanity check. So we just got some stock data from 100 symbols on the market, I think NASDAQ or Dow market, and we just wanted to see how this works with those guys. And they're pretty similar to ECG signals. They're always positive, right? Normalization might give us some issues, and there might be a little bit of bias with how it trends with the given exchange. But that's not super important for us. We're not necessarily looking for results. We just want to show that TDA with our metric is legitimate on time series data. So this is with the stock data. Right, so we normalized everything, constructed the distance matrix with Wasserstein 1, and we can see there's a lot of connected components in red, and then a few small 1 cycles that popped up. And those are in blue. So the features corresponding to those 1 cycles, or the symbols corresponding to those 1 cycles, weren't really anything interesting. So just because they're homology, or they're in the same homology feature, doesn't necessarily mean there's an underlying correlation there. And that was kind of part of our hypothesis. It might mean something, it might not. In this case, it didn't mean anything. But we can see that TDA was fine in showing that there is homology there. Maybe we can't interpret it, or maybe there is no correlation there, but there's some kind of geometric correlation, maybe not statistical or whatever. So now we're going to look at ECG signals. So once again, right, these guys might have negative values, so we just remedy this with that shift operator, and we normalize it as well. And then so the only other thing was, well, which lead to sample from. So from the 11 physical leads, we just chose one at random. Let's say we took lead 3 or whatever, and then we used lead 3 from every single patient. So that's consistent. So we chose a random lead, but then used that same numbered lead for every sample. And so with Wasserstein 1, we looked at the following homology. So the filtration value, we can see, okay, well, there's plenty of connected components in red. We can actually see a bunch of little one cycles in blue. And in the top left, we can see there were two tiny two cycles that were actually formed real quick. So that's pretty cool. So that means, okay, well, there was some kind of like geometric topological structure under this guy. So we have all these ECG signals, and with respect to Wasserstein 1, we get some kind of homology and holotopy, which is kind of cool. And so here's a little bit of correspondence. This is not necessarily like strong statistical correlation. This is just like, this is the only stuff I could glean from the output. So this is not like conclusive and not like sufficient for diagnosis or anything like that, right? This is some pretty basic observation that might not be statistically significant. So the one homology features, so these were the blue guys. So most of these patients were in one of these two age brackets, and the standard deviation of this age was around 16. And when they were in this intermediate age bracket, they were at a higher risk for atrial flutter, which is like a heart murmur. But I just thought this was interesting because these age brackets were actually non-adjacent and non-consecutive. So that was kind of interesting. I don't know if that means anything, but it was interesting. And the same with the atrial flutter. This 54 to 64 is kind of right in the middle of the two. So I don't know. There might be something there. There might not be. And then the two homology features, these were these green cycles on the persistence barcode. And so they were typically in the age 17 to 25, standard deviation of about 2.5. And then most of these ECG signals were considered above the healthy standard for their age. So once again, that might mean something. It might be nothing. But that's kind of what we got at. So I should just say, kind of in conclusion for what we did, that this, perhaps with a different choice of metric or different ways to modify the signal, or perhaps with a clustering algorithm, or there's a lot of choices we can make in TDA. And so if we did some kind of grid search or something, we tuned each of these hyperparameters, maybe we could get like actually significant, like statistically significant results from this experiment. Yeah, and then there's papers where people have successfully classified and diagnosed heart conditions with TDA, but they use some much more advanced mathematical tools that were just kind of beyond the scope of this project. But this was just kind of like a primer on TDA for time series analysis. And so what next? Like I said, this was a pretty basic introduction to TDA, but this is kind of just looking at the scope of TDA in general. See that, okay, maybe if I do more statistical analysis on the tail end, maybe that can tell me more. The choice of metric, right? TDA is very sensitive to this metric, so I could choose a different metric. Maybe I wanted to use L2 or the energy metric or something else. And then a clustering algorithm, if used at all, can also affect things. So we did not use a clustering algorithm, but that can certainly change things. In that example I was just talking about, they used TDA to extract these features that were used to inform these neural nets and other kinds of models, and were able to make accurate diagnoses of heart conditions. So TDA was just one step there of this large learning pipeline, but it extracted features, and they threw these in through a deep net, and then they were able to get conclusive information out of it. So that's pretty cool. And then TDA is still pretty young and novel, so there's tons of stuff from geometry and topology being applied to TDA, even from algebraic geometry. Like sheaves are huge. Sheaf theory is huge because sheaves kind of give us, we can have this local information and kind of look at the sheaf cohomology, can give us kind of more global information. So sheaf theory is huge. Even Lie groups and certain Lie group actions are interesting, looking at how these things change or if they're invariant or equivariant under Lie group actions. And then even crazy stuff like some Hodge theory and more algebraic geometry is being used in TDA. So yeah, it's still pretty new, pretty young, but it's showing really strong promise. Our results were nothing spectacular, but in the hands of professionals with the right tools, it is certainly showing a lot of promise and showing great and strong results. Yeah, it just might take a little bit more math to get there, more stats, more geometry, really. But yeah, so that we gave kind of a primer example, but you could for sure find some much more interesting and informative examples. So here's just a summary of my references. It's like maybe a cut off a little bit, but yeah, I don't know, that's all I have. If you actually watched this whole thing, thank you. What are we at? Almost an hour. Okay, that's not bad. I think when I did it live, it was like 50 minutes. So, not bad. Like I said, this was a little more informal, and I didn't have anyone asking me questions. It's possible I misspoke on some things or made some mistakes, and that it's take this for a grain of salt. Like I'm just a master's grad, but most of it is solid. I worked really closely with one of my advisors, and this is kind of more in his wheelhouse of research. So I'm pretty confident that most of this, most of the math and everything was correct, and hopefully my interpretation and explanation was correct accordingly. But yeah, that's all I have. Thank you if you watched the whole thing, or if you were there live. I appreciate it too. It took this was a 18-month project, kind of nonstop, for 18 months, which is kind of crazy. The programming honestly took me more time than the math side of things, much to my demise because I don't love programming and I'm not great at it. But in the end, we got where we wanted, and it's great. Yeah, it's just kind of cool to see all the work culminate and get something interesting and have something deliverable on the other side. So yeah, big thank you to my advisor. Probably not gonna say his name. I don't want to dox him. But he was great. Yeah, and I appreciate it. So yeah, thank you all. Have a great day or whatever.